I would like to thank the organizers who invited me to this conference. It is really a great honor to speak in this conference in the name of Professor Hugo, whom I have also personally learned a lot in the sense that his work and also especially his book on nilpotent groups and their automorphisms was very crucial for me in my mathematical life, and I wish him also happy years after retirement. So my title is A Generalization of the Classical Bauer-Fowler Theorem for Centralizers of Elements of Order P. And I have been this year teaching in Dresden, so this is a tentative address for me. And this is a joint work with two colleagues from Eduardo Serrati is from Dresden, and Alessandro Diogari di Burgio is visiting Dresden. So when I'm there, we started working together, and let me see. My sites don't change, okay? But do you see?
We are seeing the full, yeah. Oh, wait, yes.
Okay, perfect.
Yes, it's working. Yeah, perfect.
Okay. Let's start with the classical Fowler theorem. Of course, it is known. There is no need to remind it here. Everyone knows, but they have proved that in their very influential paper on groups of even order, which became later a cornerstone in the classification theory, they proved that every group of even order has a large proper subgroup whose order is greater than the cube root of the order of the group. In particular, they found these large proper subgroups occurring as centralizers or involutions. And if G is a simple group of even order, at that time it was not known that every group of order was solvable. But okay, if it's a simple group which contains m involutions, and n is the quotient of the order of G with m, then order of G is bounded in terms of n with this given function. Here one can observe that the argument is also related to number of involutions, not only the order of the centralizer, but the number of involutions, which is crucial in this talk. So in this paper, actually, they also conjecture that later the Fight-Thompson theorem could have been proven, and they prove, which is based on idea of counting the involutions in the centralizer of given involution. And now we can state this result as I said before, if the simple group has m involutions and n is the quotient of n, order of G with m, then G is bounded in terms of n. So they also prove that if G is a finite group with at least two conjugate classes of involutions, then the order of G is bounded by the cube of the centralizer of the involution. Obviously, any finite simple group or any group with trivial center has at least two conjugate classes of involutions. So yeah, these large proper subgroups are the centralizers of involutions, as I have said. So later, after their contribution, moreover to the contribution in the classification theory, Bauer-Fowler theorem was influential in the work of finite and infinite locally finite groups because it has other consequences. And I will present today also some generalizations of Bauer-Fowler theorem. One of them is due to Brian Hartley. This result is a generalization of this classical result for elements of any order, and not only involutions, but elements of any order, and the centralizer has finite order. So I want to state in all these results, I start with there exist an integer varied functions because I think this order of the quantifiers is important here because these functions are always uniform. So these there is an integer valued function, Hartley proves, such that if alpha is an automorphism of a finite simple group, such that alpha has order n and the centralizer of alpha has order k, then order of G is bounded by the value of f under n and k. So in the same paper, he proves the following generalization for finite groups. So there is again an integer valued function. If x is an element of a finite group such that order of x is n, and the centralizer of x has order k, then G has a solvable normal subgroup of index dividing k. And this one has a consequence in locally finite groups. Let G be a locally finite group whose centralizer is finite, then G has a locally solvable normal subgroups of finite index. Before, it was already known that simple locally finite groups has infinite centralizers, but moreover, if you have a finite centralizer, then there is a locally solvable normal subgroup of finite index. Another generalization of the Fowler theorem, there is very influential paper of Granick and Robinson from 2018. It appeared in 2020 in Journal of Algebra, but in 18 in arXiv one can find it. So in this paper, there are several generalizations of the Fowler theorem for finite groups. One of them is the following: about the existence of a particular involution of a finite group of even order. So let G be a finite group of even order, then there exists an involution X such that the index of the fitting subgroup of G is bounded by the cube of the centralizer of this involution. And on the contrary to other results, they prove another result without using classification of finite simple groups. If G is a finite non-abelian group, then there is a non-central element X such that order of G is less than 6 times CG of x cubed over 5. Before that, Hartley's results and the first result of Granick and Robinson used classification of finite simple groups, but this one does not use it. So recently, we have come across a very interesting, nice result by Skresanov, but I want to show before a little bit history about it. As I have said in the classical Brouwer-Fowler theorem, as well as the generalization by Hartley, the subgroup centralizer and its order was important. And in 1985, Strunkov proved an analog of Brouwer-Fowler theorem, showing that in some cases the order of centralizer can be replaced by the number of involutions in the finite simple group. This condition he uses is a little bit technical. I don't want to report that, but he later asked a general version of this question, and it was published in Kurko Notebook 11th edition. Is it true that for a given number n, there is only finitely many finite simple groups, each of which contains an involution which commutes with at most n involutions of the group? So recently, Skresanov answered this question affirmatively, and he proved the following result using classification of finite simple groups. Let G be a simple locally finite group and T be an involution in G. If G has at most n involutions commuting with T, then G is finite, and the order is bounded by n only. So this has also finite versions in his paper. So if you have a finite simple group with an involution, so let's restate this theorem in the language of finite simple groups. There is a integer valued function only in n, such that if you have a finite simple group with an involution with commuting with only n many other involutions, then order of this finite simple group is bounded by f of n. So after we have seen this result, the first idea that comes in mind can be to prove analogs of Hartley's problem, counting some elements instead of counting the order of the subgroup, or instead of bounding something with the order of subgroup, order of centralizer. Can we replace? Can we obtain an analog of Hartley's result with counting the elements? First question that comes in mind can be extending this result about involutions for elements of order P. So for odd prime orders, the question can be the following. Does there exist a function n such that if G is a finite simple group with an element x of order P for some odd prime P such that Cg of x has k many elements of order P? Is it true that then order of G is bounded in terms of f of k? This can be at the beginning for me something to think about. Maybe for some of the people in the audience it has very trivial answer, but I will show that trivial answer is very immediate. First, one can equivalently ask if G is a locally finite simple group with an automorphism of order P such that G has only k many elements of order P that are fixed by alpha. Is G finite? So these two can be finite version and locally finite version can be analog because these simple locally finite groups, the union of finite simple groups is a simple locally finite group. But here we have, first of all, a helpful result by Kegel-Werkowitz that first this group satisfies mean P because there is only finite many elements fixed in the centralizer, and if a locally finite group has an element with centralizer satisfying mean P, then G satisfies also mean P, another result in Kegel-Werkowitz. And simple locally finite groups satisfying mean P are classified also independently by the famous result by Belyaev, Borovic, Hartley, Schut, and Thomas. So they are simple linear locally finite groups over locally finite fields of characteristic Q different from P. So we omit the nonlinear groups then. So our groups are linear, which is a nice first step. But okay, the possible infinite counterexample of question 3 must be linear, and alpha should be a semi-simple automorphism. Semi-simple means relatively prime with the characteristic. Hartley already proved many results about semi-simple automorphisms of simple locally finite groups of Lie type. In particular, their centralizers have their fixed points have infinite many elements of distinct prime orders. But what happens if there is a prime occurring only finite many times? Namely, like in the question 3, what happens if there is only k elements of order P that are fixed by alpha? But there are some infinite examples of simple locally finite groups with an automorphism of order P for some odd prime such that Cg of alpha has only finitely many elements of order P. This comes from the existence of finite simple groups with cyclic Silov subgroups. So in the difference between prime P and odd prime and prime 2, one of the big differences is every finite simple group has a non-cyclic Silov 2 subgroup, but there are finite simple groups with cyclic Silov P subgroups for odd primes P. And for example, let's see one. Let's consider this G case, PSL2 of 3 to the 2 to the 2K. So the first one is PSL2 81, the second one is PSL2 81 square, and going so on. So this PSL2 81 has the given order 2 to the 4 times 3 to the 4 times 5 times 41. So this element of order 41 is a semi-simple element because it is relatively prime with 3. And if you are familiar with the differences between simple linear algebraic groups and finite simple groups of the type, in simple linear algebraic groups, every semi-simple element is contained in a torus, which is isomorphic to the direct product of the multiplicative group of the field. In finite groups, it is not the case. There are something that we call non-split torus. So in this case, there is a non-split torus of order 41. And actually, even G2 has also a cyclic pseudo 41 subgroup. Because if you consider the order, this order that can divide 41 again can come from the q square minus 1, and q minus 1 is already divisible. Q plus 1 is already divisible by 41. Q minus 1 cannot be divisible by 41. So, and if you consider the union of these groups, G case, PSL2, 3 to the 2 to the 2K, the union is an infinite simple locally finite group, but the maximal P41 subgroup is cyclic. So if you have a automorphism of order 41, it only fixes one element of order 41 because it should be in the centralizers, the elements fixed by this automorphism should be contained in the zero subgroup. So this is a very different situation from case 2. So at the beginning, I thought about generalizing this concept of 2 for, okay, what happens if we bound the bound the order of the automorphism by rank, and because the automorphisms of order greater than the rank would be regular semi-simple elements, and it is different, and for the smaller ones, they can have small simple groups in their centralizers. But later I thought about different versions of the problem. So therefore, the orders of the finite simple groups with an automorphism of odd prime P fixing only one element of order P can be arbitrarily large, and their union is an infinite linear simple locally finite group with an automorphism of order P fixing only one element of order P. This is very crucial difference from the case P is equal to 2. So let's try to modify the question in a different way. Does there exist a function h from n times n to n such that if G is a finite group with an element x of order P, instead of counting the elements of order P, I want to count the involutions in the centralizer. Does G contain a solvable normal subgroup of index bounded by P? This is also very easy negative answer. This answer is easier than the first one. There is this SL2Q for Q odd. As Q increases, SL2 has only one involution. It is central involution. And the solvable radical is the center. And the index of the solvable radical increases as Q increases. So the question cannot have positive answer. Okay, we cannot bound the order of the index of the solvable radical by the number of two elements. We can maybe think about this version of instead of bounding something with the two elements fixed by an automorphism of order P, let's think about the converse. Thus, there is a function, let's say G, from n times n to n, such that if G is a finite simple group with an involution, in this case, the automorphism has order 2. X, involution, I mean involutory automorphism. Involutory automorphism such that CG of X contains K many elements of order P, then is G bounded by P and K. This one can generate also counterexamples using these finite simple groups with cyclic pseudo subgroups. And you can think about this 41, or you can think about Suzuki groups, which has involutions fixing no elements of order 3 and their orders can increase. But it is not bounded in terms of 3 and 2. So one has to, if we want to obtain an analog of Hartley's result, one has to ask the question more properly, and we did that. Okay, now the function is designed to be a function of three variables. Thus, there is the function such that if G is a finite simple group with an automorphism alpha such that Cg of x contains m elements of order p and k elements of order 2, then order of G is bounded by f, p, m, and k. So when there are experts here who would answer this question maybe immediately, but since there is Hartley's result, which bounds the order of this finite simple groups in this case in terms of the centralizers, I had a very positive approach to this question. Then that it could work, and it really worked. And the proof, I will sketch the proof, and I will tell about the sketch of the proof. But first, we needed this proposition. So let's G be PSL2Q, where Q is odd, and K be the number of involutions in G. Then order of G is less than this polynomial in K. So this is an easy observation, but it was very useful in our proof. So G has a split maximal torus of order Q minus 2, which is contained in a dihedral subgroup of order Q minus 1. And dihedral groups has involutions, many involutions. How many? Q minus 1 over 2 involutions. So then Q minus 1 over 2 is less than K. So Q is less than 2K plus 1. Therefore, we know the order of PSL2. Order of PSL2 is less than 2K plus 1 times 2K times K plus 1. So if we find in our centralizer some PSL2, then we can count the we can have this bound because we can bound the involutions in PSL2 with this proposition. So maybe then it is a good idea to analyze the cases, because there is another results that give hopes, because if Cg of x contains m many elements of order p, we have already seen that at least the union of such finite simple groups, which is an infinite simple locally finite groups, should satisfy mean p. And in this case, in the union, in the infinite locally finite group, we ended up with the case that the automorphism would be a semi-simple element. And we know a lot of information about centralizers of automorphisms relative prime with the characteristic. Okay, so this is a joint work with Diogadi Burcu and Salati. And our first result in this joint work is existence of this natural valued function from n to the 3 to n, such that if G is a finite simple group with an automorphism alpha of order p, such that alpha fixes k elements of order p and n elements of order 2, then order of G is bounded by f, p, n, and k. So this has a locally finite version, of course. If G is a simple locally finite group with an automorphism of order p, such that Cg of alpha contains only finitely many elements of order p and finitely many involutions, then G is finite. So I want to give a sketch of the proof, and I want to talk about the obstacles to enlarge this result to finite groups as Hartley did. First, we have to prove the finite version. Let G be a finite simple group with an automorphism alpha of order P such that Cg of alpha has k elements of order P in G, fixes k elements, alpha fixes k elements of order P in G, and alpha fixes n involutions in G. So the result follows for alternating groups with some elementary computation. I won't do it here. For sporadic groups, there is nothing to prove because they are only finite many. So we may assume that G is a simple group of Lie type, and simple groups of Lie type over perfect fields, their automorphisms are characterized by the work of Steinberg, which in the previous talk, which was quoted. There is a very nice result. An automorphism of a simple group of Lie type over any perfect field is a product of an inner diagonal automorphism, a field automorphism, and a graph automorphism. I will explain what do they mean. So in the inner diagonal automorphism, okay, let me. Simple group of Lie type means, but okay, a simple group of Lie type means we have a simple linear algebraic group of adjoint type and a Frobenius map on this simple group, linear algebraic group. And by the work of Steinberg also, we can deduce that these Frobenius maps are the algebraic endomorphisms of with finite fixed points. So the set of the finite group of Lie type is the set of fixed points of a Frobenius map in this simple linear algebraic group, and the normal subgroup generated by all P elements here, where P is the characteristic of the field, is our simple group of Lie type when we start with a group of adjoint type, which means a linear algebraic group with trivial center. And in this case, for example, if we have started with PSLN, our group G bar of sigma, these fixed points of the Frobenius map, is PGL, and the OP prime subgroup is PSL, and the elements coming from PGL are called the inner diagonal automorphisms. So in the field automorphism of the algebraic group, field automorphism group is isomorphic to the profinite completion of the integers. But when you down to the finite group, your sigma fixes the elements in the finite group, and other field automorphism has a power equal to sigma. So in the automorphism group of the algebraic group, they are elements of infinite order, but in this finite group, there is an element of the automorphism group of the finite field P, whose some power is equal to sigma in our algebraic group. And graph automorphism is the automorphism coming from the symmetries of the Lincoln diagram. So the inner diagonal automorphisms are normalized by the other automorphisms because they are isomorphic to the group is isomorphic to the extension of some G bar of sigma with this field and graph automorphisms. And we have odd order. The case 2 is already dealt by before, so we may assume either our graph automorphism is trivial or the graph automorphism is equal to the graph automorphism of a Lincoln diagram with triviality D4. In the latter case, we can bound Q since the number of involutions fixed by alpha is bounded, because number of involutions fixed by alpha is K, but then it fixes the SL2 subgroup or PSL2 subgroup in the middle of this D4 of Q. So PSL2 has at most K involutions, and this has a bound on Q, which we have proven already with the proposition, and so we can assume delta is 1. So sorry for the notation is here. This Q should be upstairs here. So assume G is or Q prime of G bar of sigma. Q is the characteristic of the field. I don't know yet P is equal to Q or not equal to Q, but okay. Where G bar is a simple linear algebraic group of adjoint type over the algebraic closure of FQ, and G is an element in the inner diagonal inner diagonal elements of G bar sigma. Since phi is a field automorphism, some power of phi is equal to sigma in the algebraic closure. This power should be p because this alpha has order p, and G is normalized if you consider alpha to the p is equal to G phi to the p, but then this is equal to G phi inverse G phi G inverse, pardon, G phi, G inverse, G phi inverse, G square, etc. And at the end, there is phi to the p. And the first part of this expression would be 1. And since this is a split extension, and the field automorphism should have also p. So phi to the p is equal to sigma. So we have already seen that if the centralizer of an element of prime order in locally finite group satisfies min p, then G satisfies min p. And simple groups satisfying min p, simple locally finite groups satisfying min p, as we have said by the famous result of Belayev, Borovik, Hartley-Schut, and Thomas, are simple locally finite groups over locally finite fields, simple locally finite groups of Lie type over locally finite fields of characteristic Q different from P. So our alpha is a semi-simple automorphism. Some power of it is conjugate to a diagonal element of the algebraic group. So there is some technicality here, but I will try to summarize it. Okay, as we have seen in the example with PSL2 of 3 to the 4, in finite groups or in the union of finite groups, not every element is contained in the a subgroup isomorphic to the multiplicative group of the field, but in some finite Galois extension of this field, they are isomorphic. They are contained in some subgroups isomorphic to K star, and some power of its conjugate, it is conjugate to a diagonal element of the algebraic group. Then we can deduce this, and we can then compute the centralizers of these diagonal elements. There is plenty of information in the theorem in the paper by Hartley about simple groups of Lie type and their automorphisms of order P, and we can bound the sizes of the simple groups involved or contained in the centralizer, and there is a semi-simple element, and the centralizer in the algebraic group is isomorphic to a torus times some simple linear algebraic groups, and we can bound the sizes of these simple groups contained in this centralizer and the rank of the torus, which would give us some conditions on the Q or the rank. So the field parameter is also bounded by a similar argument, counting the possible simple factors that would lead our proof. On the other hand, there is a difficulty passing through finite groups, which hardly have these results. There is a difficulty passing through finite groups with the argument using the counting elements fixed by alpha of order P or of order 2. The difficulty comes from the following. When we use centralizer of an automorphism in some group can be if we have a normal subgroup invariant under this automorphism, if you have a finite group G and you have an automorphism of G, which has order n, and you have a finite normal subgroup big N of G, then the centralizer of alpha in G has order less than the centralizer of corresponding alpha bar in G over N. So when we pass to G over N with our arguments, the conditions may collapse because the elements which didn't have order P before can have order P, as in the example with SL2. In SL2, there is only one involution, but you divide it by its center, but when you divide it, there are a lot of involutions. And for that reason, it is difficult to, or it is even impossible to extend this argument to a general finite group. Neither of the arguments is Kresanov's argument or our argument. So this idea showed also us the power of Brouwer-Fowler theorem's proof, in the sense that using centralizer instead of the counting involutions was necessary and crucial. And these are my references. I would like to thank again Professor Borovic and the organizers who invited me to the conference. And I wish Professor Hugo a good retirement, and thank you very much.